I think we can start slowly, because in my opinion, the advantage of using Julia to do the programming is it provides you a high-level abstraction so that you needn't really to fully understand the lower-level hardware or whatever. And this is especially true for GPU programming. Yeah, even some participants are currently not here, but we can talk about it slowly. Some of you, I think, maybe thinking, GPU programming, it sounds complicated, but actually it's simple, at least much simpler than multi-threading when you are using Julia. So no worries, you will see that it's really simple. Yeah. And this is what I really like about to do the GPU programming for Julia. By the way, this is actually a GPU enterprise graphic card from PC2, which was broken for a long time. And Alex and I, actually, Alex, it's not my work, not break it, Abbau. I don't know how to say this. Abbau, was bedeutet Abbau of English?
You took it apart?
Yeah, thank you very much. Take apart. Yes, and we think it's useful for the courses, because normally if you buy a computer, you must have a CPU, right? Otherwise, the computer will not work. But maybe most of the computers do not really have a separated GPU. Yeah, sorry for that. And then we think it's better so that we can show you. And also, during the break and hands-on part, you can feel free to take a look or make it even broken. No worries. And I think this is useful and interesting. I think maybe we can start, formally. Let me close the door. Okay, yeah, welcome everyone. Thanks again to stay with us for this intensive course until the very last session and the very last day. This session is about GPU programming. And as I said, some of you may think GPU programming is complicated. Actually, if you are programming Julia, it's much simple. But anyway, I would like to, in the beginning, give you a short introduction. Short introduction for the comparison between CPU and GPU. And then we dive directly into Julia GPU programming so that you can program GPU by using Julia. It's very simple. And there are three ways to program or to use GPU if you are using Julia as your programming language. The first way is the so-called high-level array programming. As you can see from the name, high-level, it's a high-level abstraction. So this makes the GPU programming very easy. And I will give you first this SAXPY example using CuArray. No worries, it is much simpler than multi-threading as what I talked about yesterday. And then again, the Mandelbrot set, you will see that it's very simple. And then CUDA kernel programming. This part, I will give you a very brief introduction to CUDA kernel programming. If you really want to have the last performance from graphic card, you can also use CUDA kernel programming written in Julia. It's possible. So that you are not limited with CUDA-C, all those ecosystem from NVIDIA also. You can use Julia also do this. And last but not least, there are useful GPU libraries that you can use for your work. You can just use those libraries, and then you will have, I don't know, 5 times speed up or even 10 times speed up directly within 1 minute. I don't know, maybe 2 minutes. I'm not sure. And in the end, I will summarize for this talk. Okay, let's go. Introduction. Heterogeneous computing in Julia. So I think, in this course, you have learned that Julia code can be parallelized on CPU as yesterday and this morning by Alex. Let's say here in the middle, you have your Julia code, just a very high level Julia code. And then you can parallelize your Julia code. For example, this part, let me use the virtual laser pointer so that online participants can see. You can parallel this part, for example, like this blue arrow, to utilize multiple CPU cores, those blue squares, on one CPU socket, or even multiple CPU sockets. This is doable. But if you want to accelerate some other part, for example, more computationally expensive part, and then you can easily use Julia with minimal modification of your original CPU code to let it run on GPU. As those two graphs shows you a CPU architecture and GPU architecture from higher level. I think for CPU architecture, it's roughly self-explained. Those blue squares, you can think about it as cores. Of course, in reality, more CPU cores. And this GPU, let's say, processor looks messy. Actually, those small green dots are, let's say, the so-called CUDA cores. And as you can see, normally there are much more CUDA cores in CPU, the so-called cores, than the GPU cores. And in order to make this concept much clearer, I would like to first give you a comparison of the so-called CPU cores and GPU cores first. But no worries. This slide looks very technical or complicated, but I would like to give you a high-level understanding for the CPU. As you can see, AMD CPU currently in Noctua 2, and NVIDIA A100 GPU currently also in the GPU partition in Noctua 2, so that you have a higher level understanding. So the detailed technical name, for example, this core, those are, and CCD, those are, let's say, not really the key of this slide. Let's look at the CPU architecture first. As we mentioned during the course, one CPU socket, in one CPU socket, you have up to 64 CPU cores, from core 0 to core 63. And those cores are grouped together. First, for example, the 8 cores form the so-called CCD, and 2 CCDs form the so-called NUMA domain. And those topology, this topology of the CPU architecture is important to understand the performance. And normally, one can start 1 thread per CPU core, and in total, one socket, let's say 64 threads per socket for this socket. In practice, let's say several hundreds of threads are possible. Let's, I don't know, 100 or 200. It's possible, but not 900. 900 is a little bit too much. But anyway, with more threads, let's say hundreds of threads, there's little benefit for your calculation. Yeah, this is the key. And let's look at the NVIDIA GPU architecture. This looks even messy, but no worries. Even without understanding the GPU architecture, you can have the performance roughly automatically. This is much simpler than what I talked about, the so-called NUMA architecture and so on. So no worries. First, you see this very big die. I mean this integrated circuit. It has 108 so-called SM. SM means streaming multiprocessor. So it has 108 streaming multiprocessors. Why it is so-called streaming? Because of historical reason. You know, people try to render the graphics. This rendering procedure forms the so-called streaming pipeline. So the name is because of a historical reason. And multiprocessor means inside this multiprocessor, there are some, let's say, tiny and sub-processors. And those tiny and sub-processors, for example, in one streaming multiprocessor, there are 64 single precision unit. Those single precision unit just computing unit for single precision floating point operations. This sounds, you know, not really friendly for non-computer scientists, and NVIDIA created a name for it, the so-called CUDA cores. Yeah, as long as you remember those green small squares are CUDA cores, that's enough. And as one streaming multiprocessor has 64 CUDA cores, if you do the simple multiplication, you will see that there are, I don't know, maybe 5,000 CUDA cores. Yeah, this sounds, you know, already powerful, right? For one CPU, you have, I don't know, 64 cores, here 5,000. This sounds already powerful. And for one streaming multiprocessor, you are able to have up to 2,000. Yeah, this is 2K, but 2,000 threads. This sounds, you know, much stronger than CPU. For the entire CPU, in total, I don't know, 100 or 200 threads. But for one streaming multiprocessor, you are able to have 2,000 threads. And in total, you are able to have, let's say, 200,000 threads for one GPU. Yeah, this sounds already powerful. But in reality, you know, in reality, you need to, I'm not sure the very bottom part, but this is very important. You need tens of millions threads to have high performance. Yeah, now you realize the differences. For CPU, several hundred, I don't know, 100, 200, it's okay. But for GPU, in order to utilize the computational power, you need 10 millions. This is very, very different, you know, different order of magnitude. If you remember those two numbers, 100 or 10 millions, and then you fully understand this slide. Yes, exactly, correct. This SP means single precision. The DP means double precision. Yes, you are correct. Yeah, but no matter single precision or double precision, this is already a huge amount of cores. This sounds crazy. And then this table shows you some technical comparison between CPU and GPU. And again, no worry about those technical numbers. Those are just the numbers. So product, CPU from AMD and GPU from NVIDIA. And for CPU, you have this x86 cores, let's say 64. And for the next generation system from PC2, one CPU socket has 96 cores, let's say roughly 100 cores per CPU socket. But if we look at GPU, it does not have x86 cores, but the so-called CUDA cores. It's almost 7,000 CUDA cores. This is the differences between those two number of cores. And another noticeable differences is the clock frequency. As yesterday, I was showing you the development of the CPU frequency in the last 50 years. You may notice that from 2005, there's no increase of the CPU frequency. But anyway, it's 3, 5 gigahertz. But if you look at the GPU frequency, it's only 1.4 gigahertz. This is the, let's say, enterprise, very high-end product, but only 1.4 gigahertz. In this regard, you may think, okay, the GPU may be weaker than CPU, but actually because of the fundamental working property is quite different. The GPU power is really from massive process with thousands of CUDA cores. So lower CPU frequency, it's not a problem. And concerning the so-called last level cache, cache is important for code optimization. For the CPU, there are 256 megabyte last level cache, and for GPU, only 40 megabyte. This is much less than GPU and than CPU. Yeah, sorry, sometimes I mix those two words. And actually, what I can tell is in the early days, or even for some lower product, there's no cache at all in GPU. There's no cache because the computation power from GPU does not rely on cache. This is also a third, another third differences. And also memory for CPU memory, you need to buy separately. It's larger, 256 gigabyte. For GPU, the memory is much, not really much, but smaller than the CPU memory. But with the so-called HBM2 technique, this high bandwidth memory technique, the CPU memory bandwidth is much stronger. But those are just, the upper part are just the hardware specifications. You can forget about those technical numbers right away. Let's look at the computational performance. For the single precision peak performance, CPU can reach, one CPU socket can reach 5 teraflops. And let's look at the GPU. Even with lower frequency, GPU can be, 4 times much stronger than CPU because of the large number of the CUDA cores. And if we compare the theoretical memory bandwidth, so for CPU, it's 200 gigabyte per second. And yesterday, we talked about the multi-threading, SAXPY, the measurement of the memory bandwidth. This is almost impossible to achieve in practice. So in practice, normally 170 gigabytes, roughly 170 or 160. But on the other hand, you see, oh my goodness, GPU is 1,500 gigabyte. This is insanely difference, you see. And last but not least, the energy consumption. CPU takes less energy, but not really much less. GPU takes higher energy. But if we consider the so-called, the performance per watt, if you want to do some calculation, is this calculation energy efficient, you will realize that GPU is more computationally energy efficient than CPU. So this area shows you that if we treat CPU as a reference unit, which is 1, we will see that the single precision performance from A100 is roughly 4 times stronger than CPU. Memory bandwidth is 7 times, and in practice, maybe 10 times, for benchmarking. Yes, GPU consumes slightly more energy, but GPU delivers much higher, let's say, computational energy efficiency. And yeah, this slide is full of text. I'm not going to read this slide. There are many differences between CPU and GPU. And for you, I think most of you are not really computer scientists. I would like to highlight 2 aspects. The first aspect is the number of threads. Yes, I emphasized this point 2 or 3 times already. For CPU, the ideal number of threads is less than several hundred, but for GPU, let's say, normally greater than several millions. This is required. And yesterday, we also talked about thread pinning for CPU. This is very important, to ping the thread to the CPU cores. This is required for good performance to ping, let's say, 100 threads. This is doable by human or by some machine. But how to ping 10 million threads? It's not possible, right? If it's not possible, just do not ping at all. So this is, if the task is too difficult to do, and then do not do it. And there's no need at all to ping those threads. The hardware, design from NVIDIA will do this automatically for you to achieve high performance. So no need to ping CPU thread at all. And there's no way, think about it, 10 million threads, how to do that? This is insane. And I think for most of you, the most interesting part is suitable applications for GPU. So I think you may have the question, okay, is my application can benefit from using GPU? And then here is applications may be applications may be suitable for GPU to have noticeable acceleration if the major computation is, let's say, regular. Regular means, for example, matrix operation, like one of the audience asked yesterday, to calculate each matrix element pairwise by some operation. I don't know which kind of operation, but to do some matrix operation. This is the so-called regular computation. For sure, you will benefit the most by using GPU. And fewer random access. This is also similar meaning as regular calculation. And also with minimal conditional jumps. Minimal conditional jumps means with minimal if conditions, right, in your calculation, not so many, let's say, hundreds of if conditions. So for those applications, you will definitely benefit from using GPU. And there are some typical examples, for example, image processing and video processing, of course. Those are the so-called graphical processing. You will definitely need to think about GPU. And then very common, I think, commonly used application during our discussion during the course, linear algebra applications. If your application depends on linear algebra operations, for sure you will benefit from GPU. And the real measurement of an application would let's say, depends on the implementation. So here is the paper. This paper try to find out why some researcher or research group report 100 times faster on GPU than on CPU. So there are some also human efforts, for the optimization. But let's say if we think about the hardware differences, if your code is written in a normal manner, I mean, just like a normal behavior code, you are able to achieve 3.9, let's say 4 or 5 times faster if your calculation is compute bound, or 8 times faster if your computational is memory bound. So in general, our experience is you can definitely benefit from 5 or 10 times speed up if you are using GPU. This is a reasonable number. This 100 times faster, this is a little bit not so real. Okay, I talked about roughly the GPU architecture. Now let's just dive into Julia GPU computing directly. It's the Julia part. After understanding those differences between CPU and GPU. So Julia GPU provides you a high-level abstraction to GPU programming. And the benefit is several GPU platforms are supported. So maybe some of you remember yesterday I asked the audience which GPU are you using, NVIDIA or AMD or so. Because for Julia, you can simply write your Julia GPU code at high level, and then this code is able to be executed or be accelerated on NVIDIA GPU, AMD GPU, and also even this Mac GPU. This is possible. I'm not kidding. This is possible and doable. So write it once, you benefit forever. But for this course, we will have to focus on NVIDIA GPU because for the HPC cluster, we have this A100 available for you. And a very brief story about CUDA.jl. It was developed in 2014, roughly 11 years. It's, let's say, robust enough. And it's built on top of the NVIDIA CUDA toolkit. And you can program or use NVIDIA GPU through a CuArray or CUDA kernel. But I would like to say CUDA kernel is not the focus of the course. So if I talked about CUDA kernel, you feel boring or want to take a break, feel free to leave. I don't want to stop you because this CUDA kernel part is, let's say, a little bit too much for non-computer scientists. Feel free to do whatever you want. And last but not least, you can easily use existing GPU libraries for your applications. I don't know, for matrix operations, easily in 1 minute, and then you get speed up. So before we start, some basics about CUDA.jl. So installation, no need to repeat. And then you can use CUDA using CUDA. Yeah, naturally, use CUDA by using CUDA. And then there are some important functions to check the functionality of the CUDA device. You can use CUDA.functional if it returns true and then it works, otherwise it does not work. If you want to query, let's say to ask the detailed version information, you can use CUDA version information. And then you will see this, let's say, a very long list gives you CUDA runtime version, CUDA driver version, whatever. Yeah. So in order to make this more interactive, as you can see, normally I'm using, let's say, terminal. I do not really use Jupyter Hub a lot for my work. So this has CUDA installed. This has CUDA ready. If you type functional it works. And if you type this version info, yeah, you will see quite a lot. But I would like to highlight that I currently allocated an entire compute node for me. That is why here you see 4 devices. So in one compute node in GPU partition from PC2, it has 4 GPU, 4 NVIDIA A100 GPUs. And then the next question is, which GPU card are we using, right? Because there are 4, which one is using. And then to decide, you can just use a device to determine device. As you can see, currently the second device is using, second means actually the third. So because starting from 0, so in this way you can, make the usage of GPU more concrete. Yes, this is already some important functions on the second slide of basics of CUDA or CUDA.jl. This is a simple illustration of one compute node, one GPU compute node, and you have 2 CPU sockets, but the major part is here. You have 4 GPU available for you. This is usually the so-called device. Device means GPU. And for CPU, normally the term is host. So that the host and the device. This is, I hope this illustration is simple. And you can use the command devices, CUDA devices, to list the available devices and to show the currently selected device. I mean, the currently used device is CUDA device. You will see, okay, the 0th device is in use. So basically the first device. And if you want to use another device for, I don't know, for another GPU calculation, you can switch, use CUDA device 2 to switch. Okay, up to now, we are done with, let's say, a high-level GPU management. It's very simple, right? Just a few commands. And then high-level array programming, it's even simpler. It's even simpler because for high-level abstraction for GPU programming, you just use CuArray, this one single let's say, command from Julia, CuArray for GPU memory allocation, GPU memory initialization, to do that on your GPU. If you remember, I think maybe the first day, you have already learned array. If you write in Julia array, blah, 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 you have an array on CPU. And to create this on GPU, just type your finger 2 letters. One is C, one is U, and then you are done. And then for the computation, you need to express your calculation in terms of the array computation, right? Like array plus another array or whatever, this is why it is named the so-called CuArray or array. And also, you can call CUDA libraries directly. So there's no barrier from CuArray and some NVIDIA library. There's no barrier. There's no need to change, to do some transfer or whatever. No, you need to do nothing. That is why I feel this is much better. You need to do nothing to use NVIDIA libraries. And this may not be suitable for general computations. General computations, I mean, very general. I don't know, I cannot really name one very general calculations, but for some generic computations, maybe you need some efforts to think about it, how to do that. This is the only, point that is not perfect. Okay, GPU memory allocation, as I mentioned, you can use CuArray. For the host memory management, I think you already learned this. For example, I want to have an array of 1,000 elements without any initialization. That is why undefined floating point number. You know everything. To do this, just use this array, blah, blah, blah. And this here, underscore h, this is just a small notation for host. Just because you as a programmer, you need to have this in your mind. This is the so-called host memory. And for GPU memory or the device memory, just put capital C and U in front of it. And here underscore D means device, or you can name it underscore GPU. And then you will have this memory located on GPU, like you can see here. This is the host. This is the device, and this is really super. Let's say easy. For example, this one you just do array. Let's say on host. This is array. Yeah, maybe I make it higher so that you can see. Yeah, this is why I like terminal. I never use Jupyter, not never, but seldom. I can easily move it to the top. So array on the host, you just use the normal syntax. Array initialized with 1, 2, 3, 4, and then you have the 4 numbers that you can do with GPU with CPU. If you want to do this array on GPU, what you need to do is CU, and then it's done. And then, yes, there are some differences. You may notice, yes, this is a so-called CUDA device memory with initial values of 1, 2, 3, 4. This is very simple. So that is a huge benefit for using this so-called CuArray high-level abstraction. Just a minor detour for the so-called monitoring of GPU. So I think you are using your laptop, maybe Windows, this task manager, to see how much memory or how much processes are you running on CPU. For GPU, the same case. So you just use this NVIDIA SMI for AMD and Intel GPU, also a similar command, not NVIDIA SMI. And then you will see here is the Jupyter Hub. Here is the output of NVIDIA SMI. Maybe I can show you more vividly by switching here. You will see that, okay, here, 1, 2, 3, 4 GPUs are in use. And also the temperature, 40 degree. Yeah, this is not high because currently there's no real job running. And the energy consumption and which GPU is in use, I think this one. Right, this one, the third one, 2, because of the memory consumption, you can see 400 megabyte. And last but not least, you see that the second GPU is used. Actually, the third GPU is used. And the process name is, of course, Julia, right? Because we are using Julia to program GPU. But here, this looks strange, type C. GPU is running CPU application. This sounds a little bit strange, right? No, this C means CUDA, not CPU. Of course, NVIDIA will never put C for CPU, of course, because of business. This means CUDA. So in this way, you can monitor your GPU utilization, processes, Julia or whatever, memory usage. So this is very convenient. So let's, of course, this is also available from Jupyter Hub, but you need to open this terminal session to do that. Now the next question, as you can see, the second part of this CuArray, we only have 3 parts. No worries, this is super simple, super simple. The second part is to transfer data from host, between host and device. For example, you have some input from host, you need to put this input as input to your calculation, right? And then you need to put this through to the device. For example, the host memory has the value 1, 2, 3, 4. And then in order to put this 1, 2, 3, 4 to the device, there are 2 approaches. The first approach is, again, just use CuArray, like CPU, yeah, just the CuArray. The target variable on the device equals CuArray, and then input, and then that's it. Very simple, right? Or you can use copy, and then followed by the destination device, and then input. And then you will see, okay, now you have 3 elements, and those 3 elements, 1, 2, 3, 4, they are in the GPU memory, not from CPU. And then you can do computations about it. And once your computation is done, you know, on the GPU, and then you need to copy this back from GPU to CPU. This is also very simple, as you can see, but not use CuArray, because on CPU, there's no CUDA. You need to use the normal array, as you can see, normal array. This makes sense, right? And then to copy the device memory to the host memory, and then you have it. Or you can use, again, the copy command. Yeah, you have free choice to use. This is very nice. But what is not really perfect is the performance consideration. You need to avoid the so-called data transfer as much as possible. From this graph, you will see that actually, if the data transfer or data communication from CPU and GPU is very frequent, and then you will have the limitation of the so-called PCI Express, because the data transfer inside GPU is 1,500 gigabytes per second, but between CPU and GPU is only 31 gigabytes. So through the so-called PCI Express interface, maybe some of you are not really familiar with, you know, hardware. Me too. Alex is an expert. That's why he had this Abgebaut. Yeah. This is the so-called PCI Express. So if you need to transfer your input to GPU, you need to go through this and transfer back. You know, this is the bottleneck. This is the bottleneck. Please avoid this as much as possible. This is the key. Yeah, with new technique, maybe modern PCI Express or modern technique will appear, but anyway, please avoid go through this interface. Okay, the second part of CuArray is done. And the third part, and also the last part of CuArray is, if you want to create an array, very simple, like what I did, CuArray 1, 2, 3, 4, is done. Yes, please. Yes, this is the benefit of Julia. Julia is, let's say, very smart. Julia can determine its, can determine if this is an array or memory on the device, or if this is on host. You just use it. Don't think too much. Just use it. Just use it as simple as possible. Simple is much better than complicated. If you do not want to use this simple copy function, I know there are CUDA API which looks very complicated. I can recommend you to use this. Yeah, if you are yes. There will be. There will be, and maybe already exist. There is another GPU manufacturer which called AMD. AMD has the newer because AMD acquired the previously ATI. ATI, maybe some of you, you need to have some age to know ATI. Anyway, AMD has a so-called unified memory, which is physically available for both CPU and GPU. So this will, maybe in the future, you will never see this. So CPU and GPU will be unified. And maybe in the future, no longer a PCI Express. So those are the current limitations. I think, in the development of the technology, it will change in the future. Okay, as you can see, you can CuArray some numbers from 1 to 4, to create some initialization, or CUDA.0. I think maybe some of you already used the 0 to create an 0 array. Also works. CUDA1, CUDA random, everything works. So nevertheless, you need to pay attention to the memory allocation on GPU. Normally, you needn't to worry about it because the so-called JuliaGPU garbage collector will take care of the memory allocation. But remember, in the beginning part, I talked about for CPU, you have, 200 gigabyte or 1 terabyte or even more memory. For GPU, you only have 40 gigabyte. You only have 40 gigabyte memory for your calculation. If your calculation really needs lots of memory, and then maybe you want to, let's say, avoid the memory pressure and then release the not really used memory manually. In this case, you can use CUDA unsafe free to free the memory so that you have enough memory on GPU. Yes. This unreachable. Yes, this unreachable means, for example, if you have a function body, right? Function my fantastic CUDA code, and then inside this function, you declared some, CuArray equals, 1 to 1 million, let's say. And then this CuArray 1 to 1 million is used only inside this function. And then you have another function, let's say this function is a caller, will invoke this function which uses 1 million elements, but apparently, outside the scope of this 1 million memory, this is useless, right? So Julia will take care of this by using garbage collector to do this automatically. But sometimes this is not enough because your simulation may require much more memory, and then you can use this CUDA unsafe to release the memory manually so that you can still run large calculations on GPU. So this is the explanation. And yes, this array programming, has limitations, of course. The limitation is you need to express your algorithm in terms of the array operations. This means you need to treat this array as an entire, let's say, array or an entire thing, not as individual, array elements. If you want to access the individual element of an array, you will trigger the so-called scalar indexing. For example, here you have an array, which is 1, 2, 3, very simple. On CPU, you can simply say, okay, I want to add some number to A1. This is doable, but this is, if you are using CuArray, this is not doable. You will see this scalar indexing error, blah, 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 many errors. So this is not doable. Therefore, this array programming is most suitable for linear algebra computations like SAXPY. Or maybe yesterday from the audience who wanted to calculate the pairwise calculation, I don't know, for each element. This is suitable. Yeah, this is a suitable application. And this may be less effective for general applications. General applications means something in general. I cannot give you a very concrete example, but sometimes you can you can change your algorithm slightly and then to use array programming to calculate your problem. One example is the so-called Mandelbrot. Yesterday we mentioned. I will show you therefore quickly later on that. But first, let's take a look at SAXPY using CuArray. So basically, only one line of code, and then it's done. The others are just using benchmark tools, using CUDA. Of course, you need those. Otherwise, it will not work. And then only one line of code, and then it's done. Yeah, yesterday, maybe you saw this multi-threaded SAXPY. It's like it took several half page of the slide, but for GPU, only one line. But anyway, I would like to explain this. This Y, I think it is a vector, right? And then you need to do the so-called element-wise operations. To do that, you need the so-called broadcast in Julia. And I think all of you already familiar broadcast, basically just a dot in front of equal. This means broadcast element-wise, a dot in front of multiply, this broadcast by multiply, and then broadcast add. That's it. And you needn't even to specify the index, right? Yi, xi. No, you needn't to do that because the CuArray means you have an array. This is array, just do it. No need to think about index. And here you see something that is a little bit strange. Sync means synchronization. Here, this doesn't mean this sync has the blocking behavior, but here this sync doesn't mean the synchronization of 1 million or 10 million GPU threads. It's not possible. NVIDIA takes care of this. This sync means the synchronization between CPU and GPU. Here, this graph shows you the execution procedure. So you have CUDA synchronization. This means the CPU process or thread will offload your calculation, which is Y, this broadcast calculation, SAXPY to GPU, and then to synchronize the execution of those two parts, just being here until the result from GPU is passed to CPU, right? Because if the CPU just throw out offload the work and then leave away, and then the result, for example, Y is haven't been calculated on GPU, right? So there is a synchronization needed so that, okay, after this time, After this time slice, everything is done. You have the correct value of y. And here is just a very simple code, you know, to have large array, and then A is some number, and then use CuArray to generate memory on GPU, and then benchmark elapsed time. Benchmark also works, and then to do the measurement. So this is very simple. So the central part is only one line. Without thinking about, oh my goodness, how do I manage those threads? Is there any NUMA domain? Or are the threads are dynamically or static or whatever? Do I need to ping? You need to think about nothing, just one line, and then work is done. And the key point is the work is done in a very good shape. Let's look at the SAXPY application. The theoretical memory bandwidth means the hardware specification is 1,500 gigabyte, right? With the CuArray, you are easily, just one line of code, you are easily to achieve 1,200 gigabyte, let's say, or maybe 1,300 gigabyte per second. This is roughly, you can achieve about 80% of theoretical memory bandwidth on GPU. This is, let's say, this is really low-hanging fruit. This is really effective for your calculation. If you remember yesterday for multi-threading, I did a NUMA domain, thread pinning, you know, lots of CAM inside, and then finally, theoretical peak, I mean hardware peak on CPU is 200 something gigabyte, but in the end of the day, I can only achieve 170 or 170, 160, whatever. But here, 1,200, this is insane. So that is why I'm so happy about it. And yeah. And the next case study is Mandelbrot. Before we continue, let's recap the so-called multi-threaded computation of the Mandelbrot using Spawn. So to calculate the Mandelbrot, you have seen already the multi-threaded CPU code on multiple CPU core. The first is to compute one single pixel, as you can see here. This is the CPU code to calculate this one single pixel. What you need to remember is this is the CPU code. What does this CPU code is doing is irrelevant, because anyway, yeah, believe it or not, simple copy and paste, it works on GPU. Really, simple copy paste without understanding anything, it works on GPU. So I just want to show you, to let you keep it in mind. This is the code, that's it. And then you compute one column. For this column, of course, for this column, you have two, let's say, indices. One is for the row. You need to go through all the rows, of course. And then another one is for each column. It has, let's say, the column, the so-called Y, two loops. And for those two loops, if you want those two loops works on GPU, just copy paste. No need to understand. And on CPU, as we talked about yesterday for multi-threading, you need to do the workload distribution like this, right? You divide this full image into different threads, and each thread takes care of the individual columns. That's why yesterday afternoon we talked about two macros. One is synchronization, one is spawn. So this is how CPU works. And also, you have, let's say, good speed up with 64 threads, which is, let's say, 52 times faster. This looks great, right? most of people, they will be satisfied, but you will see something really, really interesting by using GPU. So for using GPU to compute this Mandelbrot set using CuArray, the first thing you need to think about is how to, let's say, express the computation in terms of array computation, right? Because you know this Mandelbrot is not looking like matrix multiplication or whatever. So you need to think about how to change the problem to a matrix-like problem. So the trick is, for example, the image, the final Mandelbrot inside this area, to treat this like a CuArray on your GPU. And to treat this is also very simple. You only need to create GPU memory or GPU CuArray. To do that, of course, CuArray. We have mentioned this CuArray, I don't know, many times. And then if you want to create this array like this, you need this two dimensions. One is in the X dimension, one is in the Y dimension. That is why here you have you have one for loop, but this for loop is actually two for loops. One is row from 1 to n, one is column from 1 to n. Yeah, that's simple. Here it's just initialization through the so-called Julia comprehension. Just initialize those numbers, you know, those small GPU arrays with index from 1 to n, another one from 1 to n, and then, so in the end of the day, you copy paste those codes from CPU, put it here, you have your GPU array initialized. And then the first work is done. Yeah, today I don't want to ask this question, which loop should be parallelized with GPU, because I realized that that was not a nice question for the audience somehow, especially for GPU. So to compute 1 pixel column also. But here the rule of thumb is in order to have good performance, yesterday I mentioned for CPU, maybe I think you remember you need to have a reasonable number of threads, right? But I didn't tell you what's the meaning of reasonable. So here today, reasonable means avoid millions of threads. So yesterday we said please do not generate millions of threads on CPU. On GPU, also reasonable number of threads. You know, I use the same copy paste. I like it. But here for GPU, reasonable means needs millions of threads. This is the central differences. On GPU, you must start millions of threads or 10 millions of threads. This is the needed part. And therefore, the parallelization on GPU is different. So to make this concept more easier to understand, here is your Mandelbrot set on your device. Let's say on GPU, you have done this, let's say in the last slide. And then to do the calculation, you need to start here 1,000 times here 1,000. Of course, here I cannot draw this 1,000. 1 million thread to do the calculation. And each GPU thread, like you can see, to map the calculation of each GPU thread to the computation of 1 pixel. This is what you need to do on GPU. So by doing the parallelization in this way, you have 1,000 times 1,000, in total 1 million threads, and each thread takes care of one single pixel to do the calculation. And okay, this is the last slide for showing you how to do the Mandelbrot with CuArray. This looks complicated, right? But if you remember, this part is copy-paste. As you can see, identical to the CPU code. This part is copy-paste. There's nothing new, just copy-paste. and then put this copy paste to the so-called anonymous function. And then this single calculation for each pixel will be mapped to the GPU threads for the existing CuArray. Here, this is the end of the CuArray. I didn't copy paste here, but this is the so-called image GPU to put it there. And because this is like, if you create a Mandelbrot like this image, and then to compute each pixel, this is the so-called pairwise computation, right? You just compute each element. And then you use this map and broadcast, and then you can calculate it. And this is the basic principle for the GPU computation. And on one NVIDIA 100 GPU, as you can see, you are able to achieve 6.9, let's say 7 times faster than one CPU socket with 64 threads. Yeah, this is really a lot. If you think about, okay, yesterday, with multi-threading, we achieved 52 times faster. This is already good. But on top of 52, you still have a chance to win 7 times. This is quite a lot. And if you look at my GPU CuArray code, source code, basically I used only one technique, which is copy and paste. And then this CuArray is done. Okay, CUDA kernel programming, as I said, maybe you are tired right now after I think now it's already more than 1 hour. I will just go through this CUDA kernel programming very quickly. If you found it uninteresting, you can do whatever you want. Yeah, I'm also a very flexible person. But as a warning, programming model, 6 slides, as you can see, the complexity is like magnitude orders of differences. I will go through this programming model, make it easily understandable, but no worries if you do not fully understand it. The easiest thing is to forget it. Forget it, yeah. So for the GPU parallelization, there are 3 levels. The first level is the so-called single instruction multiple threads. This is something similar to the CPU vectorization, like Alex talked about yesterday morning, the so-called vectorization, SIMD, etc. So in this part, you have 32 threads. So basically 32 GPU threads, as you can see here. Here you have one vector A, here you have another vector B. What you want to do is to add those 2 vectors together. And the first level of parallelism is a so-called SIMT. You can start 32 threads, which is much wider than CPU. For CPU, sometimes 4, sometimes 8, but on GPU, you can easily have this 32. And NVIDIA has a very special name for it. This is the so-called warp. And the purpose is to have the so-called instruction level parallelism. And the next level of parallelism is the so-called to group those warps to form the so-called block of GPU threads, right? And 32 threads forms a warp, and then you have, let's say, 2 warps. You will have 1 block of GPU threads. Here it's 64. Of course, you can have more depending on the hardware. For NVIDIA GPU, maximum you can have 1,000 threads per group. And also inside this 1,000 thread, you can also do the so-called synchronization and use the so-called shared memory to do some further optimization. But you can forget about those concepts here. And the last part of parallelization is a so-called grid level, this a grid of GPU thread blocks, the grid level, the very bottom part, to generate roughly billion, 2 to the power of 32, 31 minus 1. Yeah, this is because of some integer. So basically, you can generate billions of blocks of threads. This is a really huge number so that you can achieve massively parallelization. And this level of parallelism is not possible on CPU because of the mechanism of CPU and GPU are completely different. This maps to the entire GPU. Let's say this 1 million block maps to the entire GPU. I have a slide to definitely you can do that by using the so-called CUDA programming or CUDA kernel written completely in Julia. But for application, I highly do not recommend to do this. I will show you the reason why, especially for non-computer scientists. For computer scientists, they must understand all those things, and maybe for some chemists, they also need to understand. Otherwise, they will not have PhD. And this everything is doable in Julia. Yeah, everything is doable in Julia, but with very increased complexity. Yeah, maybe we can talk about this offline because this is really complicated. And let's move on. We still have more slides for this simple programming model. And this is a little bit too much, but let's just simply move on. One GPU thread will compute one element, like you can see here. One thread, which is green here, will calculate one element here. And then in total, if you launch this CUDA kernel, this CUDA kernel is like implicitly surrounded by a for loop so that all the calculation can be done. I fully understand this sounds strange, but this works. This is how CUDA kernel works. And this is a question concerning to why the GPU has another level, the so-called grid level of parallelism. So basically, in one word, to hide the memory access latency, because to hide the memory, GPU memory latency is the key to have performance. But as long as you do not write CUDA kernel by using C, C++, or Julia, you needn't to, you can forget about this completely. So that's why I really highly recommend just to use CuArray and then finish your work. This is really very complicated. So let's look at the hierarchy. You have one single CUDA thread, and this thread will be mapped to one single CUDA core. And then this thread block will be mapped to the so-called streaming multiprocessor. And the CUDA kernel, which contains, like this insane, not 8 thread blocks, but millions of thread blocks to the entire GPU. This is a very oversimplified, draw. In reality, CUDA allows up to 3-dimensional, those thread architecture in X dimension, Y dimension, Z dimension. So you can imagine this is really, really beyond this is complexity. And the key to the code optimization is to manage those enormous amount, really enormous amount, 10 million, 100 million threads on GPU in a proper way. This is not, let's say, an easy task. Let's just look at the CUDA kernel for SAXPY, because CUDA kernel for SAXPY is already challenging for this course. So first, using CUDA, this is the first step. And then you need to identify the so-called global index of a thread, the global index of a thread. Let's put this problem into simple. This SAXPY is just a one-dimensional problem. And then to identify the global index of this thread, you need the index of this thread inside one block, right? This index of this thread inside one block. And then you need to know the block dimension of this thread block. And then you need to know the index of this block. And then you can find out the so-called global index of this thread. But keep it in mind, this is only for one dimension. CUDA supports 3 dimensions. So you can imagine the first step is already complicated. And afterward, in the end of the day, you identify the so-called global index of this thread. And then, for example, here, the thread, the index of this thread is 1 for this small block. And the block dimension for this is 128, because here, 128. And then this thread block belongs to the first block of this thread grid. This is the visualization, simplest visualization. And then you can calculate this global index and then put it to the next step to calculate the individual element. And this will be executed by GPU thread, and as if this line is surrounded within an explicit for loop. And then you need to execute this CUDA kernel. To do this, anyway, you need to the first part is just the preparation. Anyway, you need to allocate the data on the host and the GPU device. Those are very easy, right? Just the array or CuArray do the allocation. If you are using CUDA-C or CUDA-C++, the API function name is much longer than this CuArray. It's much longer. And then copy the, copy the data. And then you need to define the so-called GPU execution configuration. How to launch the CUDA kernel. And to define this so-called GPU execution configuration, you need to specify the number of the threads for one block and the block size and also the dimension of the grid. But this is only for one dimension. If your application needs 3 dimensions, this will be super complicated, which means here is not 1, here is not 1. You need some other numbers. And then you can launch the CUDA kernel with the previously defined so-called execution configurations, and then to launch this kernel with the configuration for thread, with the configuration for the block, and then use CUDA sync, again, this CUDA synchronization to execute this kernel to ensure that you have the result. And last but not least, you need to copy the data back to the CPU host. After showing you this very complicated procedure, I think at least you believe me why I recommend you to use CuArray. Don't go this way. Don't do this. I'm showing you this. Only I want to tell you, do not do this.
So what is like complicated about this finding imagination of this medium thing? Like, why do you think that it's so complicated other than like,
It's complicated because you need to take care of lots of technical details by hand, by yourself. For example, you need to take care of the dimensions by yourself. You need to take care of how those threads are arranged by yourself. So this is, I think, one major reason of the so-called complication. And I will show you in a few slides. Maybe some of you may think, okay, with those complicated code, I'm able to win very good performance. No. Very complicated code does not guarantee good performance. Does not guarantee good performance. This is a misconcept. I will show you later on. That is why, I show you lots of things just to prevent you use this CUDA kernel. Okay, after showing you, some complicated things, now you have some speed up. Yes, 7% speed up. This is CuArray. This is a benchmark. The theoretical memory bandwidth is 1,500 gigabyte, right? This is a hardware limit, like speed of light, no way to go beyond it. And previously, we just write CuArray, just the one line of code. You have 80% of the theoretical peak. Now I talked about, I don't know, I'm tired. I talked about roughly half hour about this complicated CUDA kernel. You have 7% improvement. Do you think this is worth our time? No, I don't think so. If the improvement is 70, I'm happy. Only 7%, let's forget it. There are improvements, that's good, but only 7%, this does not work well. And I will show you another, let's say, configuration or so-called optimization will make the CUDA kernel even slower than the CuArray, programming. Okay, performance tuning for CUDA kernel. As you can see, it's already very complicated. So you can tune the dimension of the threads, the thread blocks, or the dimension of those blocks. Yeah, you can tune everything to change the number of threads and the number of the thread blocks. There are multiple combinations. It's, let's say, not straightforward, but in the end of the day, all those efforts, let's say 30 minutes or half hour talk, may not give you good performance. This is not guaranteed. Let's look at this first, this red line. This red line plot, this CuArray, this red line plot. This is already good, let's say. 80% hardware theoretical bandwidth. This is already good. But if there are some CUDA parameters or, I don't know, some configurations, low-level technical things is not tuned properly, you will have only 500 gigabyte, 500 gigabyte GB per second, like this green line with this kernel. This is, I don't know, maybe 40% performance of this super simple CuArray code, right? If you do some further tuning, maybe you are able to achieve this purple line, which is 1,000 gigabyte per second, but still slower than this CuArray coding, right? And then with other tuning parameters, you are able to be better than this CuArray code. But as you can see, the difference is only 7%. This, das lohnt sich nicht, ja? Das ist ganz einfach. I don't want to say more. This is not really useful for non-computer scientists. Yeah, for computer scientists, they must achieve this best performance. Otherwise, you know, there is a different requirement. But for most of you, I think this is CuArray programming is already good enough. And last but not least, let's move quickly to the GPU library. If you are using Julia, you can easily use other available CUDA libraries like cuBLAS, cuFFT, you know, this fast Fourier transform, random number, whatever solver. You can easily use it only with one line of code. For example, I think most of you may know the so-called matrix multiplication. And to use it, you start with CuArray or CUDA-array, whatever, on GPU, and then just call cuBLAS general matrix multiplication, and then it's done. And this will call the cuBLAS library directly in cuBLAS. This is very convenient. And the very first part, CUDA synchronization, only ensures the, you know, the synchronization between host and device. But very important fact is, with this one line of code, you are able to achieve 98% of the hardware performance. You know, this is really high, 98% of the hardware performance. So recommendation is very simple, just use library if it is possible. Don't try to write your own CUDA kernel to compete with NVIDIA. Yeah, normally it's possible, but very difficult. So summary, for this 90 minutes, first we talked about the CPU-GPU architecture. You can forget about all those numbers, but one number that you should not forget is on GPU, you need tens of millions threads. If you try to use 100 threads on GPU, and then I'm pretty sure there's no performance at all. You need to think about how to, let's say, express your application in terms of millions of threads. This is the key. And but anyway, I would like to say not all applications may be suitable for GPU architecture. You need to think about it. But I think for most of you, you know, during the last 2 or 3 days, we talked about exchange the idea. I think most of you may use matrix operation or pairwise matrix whatever. So if this is the case, yeah, definitely you are guaranteed to have good performance with GPU. And for CUDA.jl, you can use the high-level abstraction, the CuArray. Yeah, the syntax is very simple, and the performance is also, let's say, reasonably good. Yeah, reasonably good. And yeah, this is apparently the slide from Christian Please, Professor Pleise. For computer science scientists, they need to write CUDA kernels, but not really for you. Yeah, you can forget about CUDA kernels completely. And last but not least, use GPU libraries. If it's available, just use GPU libraries. Do not try to write your own CuArray, whatever, just use the GPU libraries. And yeah, this is based on the lecture from Professor Pleise in the high-performance computing oder Einführung in Hochleistungsrechnen. And last year, Marius Meyer was also contributing course materials. And last but not least, yeah, most of you do not really do atomistic simulation. But actually, I'm one of the organizers for this international autumn school in CB2K and GOMAX. If you know someone who is running simulation in quantum chemistry or solid state physics, yeah, you are welcome to register. And this is, again, free of cost. Yeah, thank you very much. I think that's all for today. Yeah, so any question?
I have a question.
Yes.
Yes. First of all, thank you very much for organizing this workshop. Over the past few days, we've learned a lot of techniques on optimizing our code. Like, let's say someone has a project, like has a code that they've made, and now they want to optimize this code. Like, in which like order would you recommend, like, which strategy to pursue first? Like, say programming with GPU first, or with MPI, and then um, uh, um, single multi-threading, and then last but not, and then at the very end, they program, or they do this high optimization techniques that we covered on the very first day.
Oh, yes, this is a good question. If you are starting with a software project, you want to improve the performance, how to do that? So the first step is to profile your application with an example input. Why it is important? Because you need to have the profile of your application, and then you understand where is the bottleneck. Yeah, this is very important. Understand the bottleneck of your software, or understand the bottleneck of your application, and then focus on this bottleneck. Yeah, because the bottleneck is the key. For focusing on the bottleneck, there are several techniques you can think about. For example, multi-threading, but I do not really recommend. Or MPI, like Alex mentioned this morning. This is also doable, or GPU, but this depends on the character of your bottleneck. If your bottleneck calculation is matrix multiplication, yes, like yesterday, one of the audience asked, no question, just use GPU, or maybe more GPUs, multiple GPUs. But if it's like tree search, I'm a fake computer scientist. This binary tree search, if it is the case, the bottleneck, better not consider GPU, better consider, let's say, multi-threading or even MPI, to divide this tree into several subtrees. This highly depends on the, highly depends on the real character of the bottleneck of your application. So there's no easy or unified answer. But first, do profiling. We didn't cover how to do profiling in Julia during the course, but it's doable. You can use Intel VTune or so to do the profiling, and then you know where is the bottleneck, and then how to do that. This can be another course, let's say, another 2 hours course. Yeah, I hope this 2 minutes short answer makes your question a little bit clear.
Yes, it has. Thank you very much. Because in my case, I've done this profiling for my particular case, and I found that the bottleneck in my case was some heavy linear algebra operations. So in this case,
Sorry, what?
yeah. Because okay, can you hear me?
Yes.
Yeah. So the first, like in my case, the bottleneck, I found it to be this heavy linear algebra operations. So in this case, you would, but based on what you recommended, I should first start with using GPUs for programming with
Yes,
GPUs
yes, yes.
to make it go faster, the code.
Yes.
All right.
If the bottleneck is the dense linear algebra operations, go GPU for sure.
All
And
right.
maybe in the future, Alex and I, we can do MPI plus GPU. This is also doable. Use multiple GPUs with MPI. This is also doable, but not covered by this course. Yeah.
Okay. Thank you very much.
Yeah, you're welcome. Yeah, if there's no question, we can take a break. Yeah, thank you very much for staying with with us, with Alex and I, for such a intensive course. Yeah, let's take a break.